Hi, this is Margaret. Last time we talked about power transmission lines and substations. Now let's talk about how power gets from the substation to its final destination over these distribution networks. And by the way, when you think about voltage level, you hear people talk about low voltage. In the context of power generation and distribution and motors, low voltage means it's less than 600 volts. And then we get from there into the meter on the building. So these distribution lines can be underground, and you especially see that in cities. This has a lot of advantages. You're not vulnerable to power outages when a storm comes through. You don't have trees getting butchered because they ran into the wires. You reduce the visual clutter, so it's a good solution. The thing is, it costs about 5 times as much to install initially as the overhead wires do. You will still see these on-pad transformer boxes. And by the way, these are a standard green, just like the insulators on the transmission lines are sky tone gray to blend in with the sky. These are a kind of a grass green color to blend in with the landscape, and there's a specification for that color. So these lines can be overhead, which is easier to install, lower cost to install. On the other hand, you get visual clutter and you get damage from storms. Let's look at what's on a pole when we are above ground. There are rules that govern what can go where, and these upper layers are for the utilities, the power lines. Communication lines go on the lower layers. And then there's required to be an open space, 40 inches I think, in between the power lines and the communication lines, and that's for the safety of the communication workers. All right, so on the power line, up at the top are the 3 primary lines, and you'll by now recognize that they come in 3. And there are big insulators. They stick out from the side, unlike a transmission line where they stick down. And then there are various kinds of protection and cutoffs, fuses, cutoff switches. See the little loop there? You can take a tool and reach up and open it if you need to turn the power off. Then between the main power line here and the secondary line that's going to go to a building, in between those are the transformers. And again, notice the sets of 3. The transformers connect the primary and the secondary. And then every few houses will share several transformers. This levels the load. So below the transformers are the secondary lines, and below that are the lines for street lights. And these secondary lines might go through rubber spool type things, or they might be carried on what are called messenger wires, where the messenger wire is pulled tight. The actual conductor gets a little bit more looseness to allow for flexing and temperature changes. And then street lights get their power from the secondary circuits, and I'm sure you've seen these induction loops in the pavement. Those are kind of interesting. Then down below that are the communication lines, and these are big lines, and we might think, oh, well, that must be high voltage. No, it's not. It's low voltage. The conductors themselves are aluminum again, and they come in 3s. And there's a danger of fatigue caused by vibration, and fatigue is a failure mode caused by reversal. So it moves back and forth, back and forth. You can see that if you try to break a paper clip by bending it back and forth. So they have various devices to deal with to prevent that fatigue. Here are 3 of them. Then under the primaries is a smaller fourth wire, that's the neutral wire, and you probably know by now that every circuit has to have a complete loop in order for current to flow. If you don't have a closed loop, you don't have current. So the neutral carries that flow and balances out the load. On power poles, you will see these things sticking up, and if you see them in sets of two, you are looking at a recloser. It's kind of like a giant version of a ground fault circuit interrupter in your bathroom, where if there's a circuit fault, it automatically shuts off the power. Well, that's what these reclosers do. And they're automatic, so if there's some problem in the circuit, they'll automatically cut out, but then they'll automatically cut back on again. And they'll do that 3 times. If there's a failure more than 3 times, then they're automatically in the off position, they're open, and someone has to come and manually reset them. When you're in a storm and you see the lights flicker, 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 that's not the transformer, that's these reclosers trying to deal with the circuit faults. Then down below the secondary lines are the communication lines, and they can be closer to the ground because they're at a low voltage. They will be carried on messenger wires, and you'll see loops in the communication line to accommodate things like vibration from wind and temperature and so on and so forth. And you'll sometimes see these less and less often nowadays, but you still see them. These big boxes on the communication lines. I used to think, oh, that must mean this is a big power line with something powerful going on in there. And it turns out, no, it's not. That's just a splice. It's where 2 lines are joined together, and then they put a big plastic housing around the outside to protect the splice. So that's what that is. Then you see these diagonal wires called guy wires that stabilize the pole. And every pole has to have a ground wire. It's copper. It runs along the length of the wire. Every substation has grounds too. Here's a fence post at a substation with a ground wire. And then there are also some shielding devices in their metal fences. Here's the reason for grounding. So current, and you know that current is flow. Current is the flow of electricity. So current always flows along the path of least resistance automatically. Now, there's always a little bit of current flowing through the surface of the earth. My electrician instructor taught me that. And everything's fine unless you get, let's say, a break in the insulation. So here's a piece of equipment. This is supposed to be a person. Here's a piece of equipment, and let's say there's some break in the insulation. So the rubber went away and it's not protecting you anymore. What is the current going to do? It's going to flow through the path of least resistance, which in this case would be you going all the way down to the surface of the earth. You don't want that. That would be bad. So a ground is a copper wire that gives the current a direct path to the ground, to the surface of the earth, and it's an easier route than going through you, so the current will flow through that and not through you. Or alternately, it will not flow through your equipment and blow something up. And grounding is regulated by the National Electrical Code. There are certain ways we can do it and certain ways we cannot do it. There's grounding and there's bonding, and you might want to go dig out your electrical code and see what it says about these. If you want to talk a little bit more about circuits and grounds and panels and so forth, we don't talk about house wiring in this class, but there is another class called Architectural Plans where we talk about electrical wiring, and you might want to go have a look at that. You have access to all those lecture materials because you're a student, so go have a look if you'd like to know about house wiring. All right, next time we're going to look at some of the symbols we use in making a drawing for power distribution.